Hi, thanks for coming to my talk. I'm sorry I can't be there in person or live, but please feel free to ask questions in the forum associated to this special session. I'm excited today about telling you about Clausen's formula and high Picard rank K3 surfaces. This is a project that I have been working on with Ursula Whitcher, who is at Mathematical Reviews at the American Mathematical Society. This is something we've been working on for a few years. This is us at the Fields Institute working on this project. And so let me tell you a little bit about it. So the first thing is, I think one important thing about every talk is if you can understand a little bit more about every word in the title. So I first want to tell you about K3 surfaces. So they're actually named after these three mathematicians, Kummer, Kähler, and Kodaira. If you didn't know, unfortunately, Kähler was a pretty serious Nazi. So, you know, sometimes we name things after people and they're not very nice people. But this is the naming origin of this. And it's also sort of a reference to the mountain K2, which is a mountain in the Himalayas that is considered to be one of the hardest to climb. And so a sort of an idea of like, you know, naming it after this like peak of knowledge or something. But there's actually a mathematical definition. So K3 surfaces over the complex numbers are just a simply connected, compact, complex surface with trivial canonical bundle. And they are all diffeomorphic. Now, this might mean something to some of you and not to a lot of you. I actually found that understanding K3 surfaces was easier with some examples. And so here's some examples of what we mean. So this is like in one dimension, this definition basically translates into an elliptic curve. In two dimensions, that becomes the K3 surface. Or the one-dimensional version of a K3 surface is an elliptic curve. And like a three-dimensional version of this is a Calabi-Yau threefold, which is really interesting to physicists. And so if you get confused about what K3 surface means, think about like a two-dimensional sort of generalization of things we like about elliptic curves. But the part that we're generalizing about the elliptic curve is not the sort of group. That's what you would need. If you went in that direction, you would get an abelian variety. But what we're really generalizing is this sort of trivial canonical bundle in this sort of one holomorphic, unique holomorphic one form. And so this is the idea that we want to generalize. And so, but associated to the K3 surface is this thing called the Picard group. And so it's, if you are familiar with elliptic curves, this is the same as the Néron-Severi group, which is all the divisors up to algebraic equivalence. In this case, divisors are actually these curves. Okay, so the Néron-Severi group of a K3 surface is a free abelian group with rank between 0 and 20. Okay. Another thing I want to tell you about, just to get like the ideas established of where we're going, is this idea. So this is sort of a tangent, but the idea of a symmetric square. So a symmetric square, well, so first of all, if you have a homogeneous linear differential equation with coefficients in the complex numbers, or in rational functions with complex coefficients, there exists a homogeneous linear differential equation such that if there exists a homogeneous linear differential equation with coefficients in C of t, such that the solution space of M of y is the C-span of these actually like pairwise products of the solutions of L. And then what we say is that M of y is the symmetric square of L. Okay, so then a differential equation can be a symmetric square of another differential equation. Okay. And so here's the big thing. I have told you a little bit about K3 surfaces, a little bit about Picard groups, and a little bit about symmetric squares. And all of this comes together in this beautiful theorem by Chuck Duran from his PhD thesis that says that the Picard-Fuchs equation, a differential equation that encodes some of the geometric information of a variety. So the Picard-Fuchs equation of a family of rank 19, remember, Picard group is between rank 0 and 20. So of rank 19, lattice polarized, if you know what that means, great. If not, that's not going to be a huge deal. K3 surfaces can be written as a symmetric square of a second order homogeneous linear Fuchsian differential equation. Okay. And so that is sort of the big thing that puts everything together. So if you know that your K3 surface is rank 19, lattice polarized, then you know that the Picard-Fuchs equation, which is this equation that collects information about the geometry, is a symmetric square of a simpler differential equation. Okay, so that's super cool. The moral, as I just said, is that the Picard-Fuchs equation of a family of Picard rank 19 K3 surfaces looks like the symmetric square of the Picard-Fuchs equation of an elliptic curve. Okay, and this is really nice. This is as nice as you can get. So here's another thing that we're going to need just to get like a sense of where we're going. So far, this is the first time you've seen a finite field, so that's exciting because this is a finite field session. If we have a smooth variety over a finite field, then we can define something called the Frobenius operator, which induces a p-linear map of the nth cohomology to the nth cohomology. Okay, and this Hasse-Witt matrix, or holomorphic n forms to holomorphic n forms, really, and these are vector spaces. Pick your favorite like cohomology definition that works with a finite field. I mean, I don't mean de Rham cohomology here. I mean something that makes sense over a finite field. And the Hasse-Witt matrix is the matrix that defines this sort of linear vector space map, okay, linear transformation. So you pick a basis and you can find your Hasse-Witt matrix. Somehow that is telling you information of what is like the piece order Frobenius, this idea of like raising things to the p, okay? For Calabi-Yau varieties, of which K3 are an example, so if you have an elliptic curve, a K3 surface, or a Calabi-Yau variety, we actually have that this, because this is what the definition I gave you at the beginning or mentioned, that the holomorphic n forms is just one dimensional, okay? And so this is a one-dimensional vector space. And so the matrix is not really a matrix, it's a 1-by-1 matrix. So it's actually a Hasse-Witt constant, right? We still use the word matrix throughout because there are generalizations that make this way more interesting and more complicated with an actual like matrix instead of just one constant. So in fact, when you see Hasse-Witt matrix in this particular talk, because we're thinking of K3 surfaces, you should think of a constant. And so nice things have been figured out about Calabi-Yau varieties and their Hasse-Witt matrix. So Nick Katz came up with a famous congruence formula. Don't have time to give you all of the details, but I'll just say that he figured out that the number of Calabi-Yau of points on a Calabi-Yau variety mod P is determined by the Hasse-Witt matrix. Okay, so this is the Hasse-Witt matrix tells you everything you need to know about the point count. And now we're getting more into like finite fields, like, well, why would you give this talk in a finite field session? Because we're looking at solutions over finite fields. And so, and he in fact did most of this work, or his work this idea using the Fermat pencil, or what he calls the Dork pencil, which is this sort of pure powers like x naught to the n plus 1, etc., minus this monomial deformation. So this is why I called it Fermat, is because you just have like each variable to the nth power, right? And so that hypersurface, if n plus 1 and p are relatively prime, then the Hasse-Witt matrix is actually a truncated hypergeometric series. So hypergeometric series are particularly nice. They have all these nice properties. And in particular, hypergeometric series or hypergeometric functions are very closely related to very nice differential equations. And so now we're starting to see maybe where we're going. And so for the Fermat pencil of Calabi-Yau hypersurfaces, the Picard-Fuchs equation is a hypergeometric differential equation. A solution to the Picard-Fuchs equation is a hypergeometric series, and the truncations of this series give us our Hasse-Witt constant or Hasse-Witt matrix. Okay, so now we're starting to see, hopefully, that there's some connection between the Picard-Fuchs equation that we were talking about at the beginning with this sort of nice point counting fact or function. And so one question is, can we do this over toric varieties, right? Like all of the stuff that I've told you about is in these like sort of nice hypersurfaces. And so Fritz Beukers, Masha Vlasenko, and Shenglong Yu have been doing some of this work. And I want to tell you about what I've been doing with Ursula, but we've been inspired a lot by those three folks. And so and this is also based on some work that Ursula did with an undergraduate student of hers when she was at the University of Wisconsin at Eau Claire. This was Chris Magyar. And so these are images that they came up with. And so what we're going to look at is a grouping of what we call combinatorially equivalent K3 surfaces. I don't have time to tell you about this, but I might tell you about this in a different talk, that we can define K3 surfaces or toric from toric information. So we can go from a polytope to a toric variety, and then we find a hypersurface in that toric variety, and that is a K3. And there are nice ways of visualizing this. For example, all of these polytopes are related to a K3 surface that we're interested in, okay? And we can group them in a way that we say are combinatorially equivalent. And I'll tell you a little bit about that. And so here's a previous result from work that I've been doing with Ursula, and this is on the archive. All of the polytopes that I showed you in the previous slide correspond to families of K3 surfaces in toric varieties that have the same Hasse-Witt matrix and point count mod P. Okay, so somehow we've been able to group them in ways that we know they have the same Hasse-Witt matrix and thus the same point count. Now, the polytopes that I showed you, maybe let me go back a little bit. So these have all been classified in 3 dimensions. There's like 4,800 of them or something, but they've all been classified. So there's like databases of them. For example, Sage knows when you say polytope 3, it knows you mean this one. If you say polytope 4,283, it knows it's this one. So these are all going to be associated to the same Hasse, or are going to have the same Hasse-Witt constant. Here are the 2 varieties that one can construct from those 2 polytopes. So these give you K3 surfaces in a toric variety. Notice that one of these is way more complicated than the other. So in fact, like this idea that we know that they all have the same Hasse-Witt matrix and the same point count means that I can calculate this mess, the point count for this mess, by using this much simpler hypersurface. So that's super nice. And so here's the story. So we're going to focus on this grouping. So for polytope 3, we can do a process called the Griffiths-Dorff method to find a Picard-Fuchs equation. and this is what we get. So remember the Picard-Fuchs equation will have like, you know, coefficients in C of t. In fact, this is like Z of t. And this is, after some work, equivalent to a hypergeometric differential equation satisfied by this hypergeometric function. Haven't defined hypergeometric functions, but these are power series in this variable, and they have coefficients that are sort of determined by factorials of these parameters. And these parameters sort of determine everything you need to know about the hypergeometric function. And so there's some work we need to do. I haven't told you about HLYY, but like we need to expand around a point of maximally unipoint monodromy. This is all advertising for my talk next week. So I'll tell you more about that then. But you can associate it with this hypergeometric equation, and through a change of variables, you can get this hypergeometric equation, which is just a little bit nicer. And in fact, this is the one that's related to the point count. So the point count is, remember, there's this Hasse-Witt matrix that is related to a hypergeometric function related to the Picard-Fuchs equation. And now the point count is exactly this. It's 1 plus this hypergeometric function truncated at the p-1 term mod p. Okay, so this is our finite field point count. And so here's the upshot. We extracted arithmetic information. In general, counting points on K3 surfaces is very hard. But using information about the periods or the geometry of our variety, we can extract arithmetic information. So this Picard-Fuchs equation is determined by the periods. And we can do this for multiple related families. So this was the grouping of toric varieties that I showed you. And so this is a sort of like the big sort of exciting thing for us. And so here's a fun hypergeometric fact. So somehow I have to tie it into like the stuff that was happening in the beginning, right? Like good storytelling. I showed you the gun, it needs to go off in the third act. And so Clausen's identity says that if you have a, that this hypergeometric function with just these three parameters squared is the same, this squared is the same as this sort of more complicated, this 3F2 hypergeometric function. This is a very old identity. And for our Picard-Fuchs equations, this is true. So this is the one that we got for the point count on the right. And so on the left, you see that this is some other simpler hypergeometric function squared. Now you should be thinking about what happened at the beginning of this talk. So what happened at the beginning of this talk is what we thought was our theorem was that if you have a pencil of K3 hypersurfaces in a toric variety and that the rank is 19, so this is because of Chuck Duran's theorem that I showed you earlier. If you have a Picard-Fuchs, a K3 hypersurface of Picard rank 19, then you know the Picard-Fuchs equation is a symmetric square. But we just showed in the previous slide that like every one of these hypergeometric functions is a square. And so ideally you would think that the Hasse-Witt matrix then is, because it's associated to that hypergeometric function, is a quadratic residue. And so it's always a square mod p. That would have been nice. That is not true though. We actually, as one should, plugged it into Sage just to see some examples, and we actually saw that this was not always true. For example, when p is 11, this is only true for parameters 3 and 7. Okay, so no, not a theorem. So here's what we've been thinking. So the Picard-Fuchs equation is a symmetric square of the Picard-Fuchs equation of an elliptic curve. All the things that we're looking at are rank 19. The equations are definitely hypergeometric also. So they satisfy Clausen's identity. But this is all happening over C. So something interesting is happening when we're switching from complex numbers to finite fields. The Hasse-Witt matrix is definitely of this form, mod P. And so what we found is that this sort of modified theorem, so that if we have rational coefficients and the Hasse-Witt matrix is a quadratic residue for every prime p, but with some restrictions on which primes. Okay, the primes have to be such that we have a character of the right order in the finite field, and we don't always do that. But we think that something is true more generally, and we've been working on some additional stuff. And so we have a finite field version of the Clausen's identity, and there is a finite field version of hypergeometric functions. So right now we've been doing sort of like all this over C and then translating mod P, but it might be smarter to work over a finite field. And again, like these characters might not exist, but one can hope to extend these things. And so that's what we're working on right now. So this is sort of work in progress. So post the paper that I shared with you before that's on the archive. And so if you want to know more about like how we got there, I'm actually going to do more about the stuff, the number theory side and the toric variety side in the number theory in the Americas session. And my talk is going to be on July 22nd from 6 to 6:30 Buenos Aires time. So, and it's called Hasse-Witt matrices and mirror toric pencils. And so it's going to be related, but I'll tell you a little bit more about like sort of why we found that those varieties were related and how we got to those groupings that then turned out into like these really fun hypergeometric identity chasing. And thank you so much for coming to my talk. Gracias, obrigada, and merci. I hope you're having a wonderful time at our virtual Congress of the Americas. Hopefully next time we'll be in person. Bye. Thank you.